Start recording. Good stuff. Okay. Nobody had any questions? All right. Then we're going to move today on to percent purity. This is on page, I think it's 74. 74. So percent purity, many chemicals are not pure. Percent purity is important because when you make a compound, you might have some impurity. It's not on. Oh, thank you. Okay, 74, I think. Yeah. Okay. So anyway, you might create a chemical and you want to keep the purity, like the impurity, down below a certain level, right? Because you don't want to make things that have like contaminants in them, or at least, keep it as small as possible. Or you might need to know how much of a particular ion is dissolved in water to find out if it is within the legally allowed level. Yes? So here is how we calculate percent purity. We take the mass of the pure compound. Okay, let's bring up all my pens. We take the mass of the pure compound in the impure sample. I don't know what color I want to make that, so I'm not going to. Okay. Over the total mass of the impure sample. So what we've got then is we have, let's say for example, here is our sample. This is our impure sample. And most of it is the pure compound. But some of it is the impurity. Now, it wouldn't be blocked out like this. It would be like mixed in, but I just want to make it really easy to see. So let's say we had 9 grams of the pure substance and 1 gram of the impure substance. What that would mean is that our impure sample would be the whole thing would be 10 grams, yes? So we're going to take the mass of the pure compound, 9 grams, and divide by the mass of the whole thing, the impure sample. Okay, and so that's going to be 9 grams divided by 10 grams gives us 90% pure. And that's what percent purity is. Okay. If an impure sample of a chemical of known percent purity is used in a chemical reaction, the percent purity has to be used in your stoichiometric calculations. So if you have a reactant that's only 90% pure, you're only going to get 90% of the product that you think you're going to get. Yeah? Because if I'm reacting my pure stuff right? And it reacts with the other reactant. 1 gram is not going to react, right? Because it's something else. It's something else that doesn't react. Does that kind of make sense? Yeah, okay. We'll do an example. Hopefully it'll make more sense once we do an example. So let's consider the reaction of magnesium hydroxide with phosphoric acid. We have ourselves a lovely little what type of reaction? That is a neutralization, yes. Okay, and we want to know how much Mg3PO4 we can make, assuming that we get 100% yield, okay, from the reaction of 15 grams of 92.5% pure magnesium hydroxide. So what we have is we have the impure sample of magnesium hydroxide, and 92.5% of that is actually MgOH2, and the other 7.5% is junk. Yes? So, is the entire 15 grams going to react with H3PO4? No, only 92.5% of the impure sample will react. And what does the word of mean? Of means times. So guess what we do? We take 0.925, right? We change it into a decimal, 0.925. Of the 15 grams. And we get 13.875 grams. So this magnesium hydroxide is actually just 13.875 grams. And then the question asks us, if that's the amount that we have, then how could we, how much Mg3PO4 could we make? Okay. Oh, that should be Mg3PO4 too. Oopsie. Fix. Okay. Anyway, then it just becomes stoichiometry calculations. Yes, we have our grams of MgOH, and to find out the MgPO4, we have to go through the mole. So we change that to moles of MgOH2, and then we change that to moles of Mg3PO4, and then we change that to grams of Mg3PO4, and that gives us our final answer, which we then put to correct sig figs. Is good? Okay. So really with a question like this, there's not actually much that's new. What's wrong with my voice? There's something in there. Okay. We'll give it a go. We'll see how it goes. Yeah, that's strange. And that just happened in an instant. Super exciting. Oh, it seems to be coming back. All right, good. So we have, it's just really reading the question and determining what it's talking about. Does that make sense? So it's kind of like just figuring out what the question is asking. So here's another type of question you might have. You might calculate the amount of an impure reactant needed. Okay, amount of impure reactant needed. So we want the mass of the 88.5% pure MgOH2. So that's our impure MgOH2. I know it's weird to say it's impure when it says pure, but it's just 85% pure or 88.5% pure. So it's impure. Did that make any sense? Okay, good. And we want to know how much of that we need to make 127 grams of Mg3PO4. So let's just figure out how much MgOH2 we need to make that amount of Mg3PO4. So that's just a straightforward calculation. So this is how much pure stuff we need. How much pure MgOH2 do we need? We go from magnesium phosphate, grams, to moles of magnesium phosphate, to moles of MgOH2, to grams of MgOH2, and we end up with this. This is how much pure MgOH2 is needed. So we can visualize this once again, kind of with our little, sample. This is our impure. MgOH2. And we have, I'm just going to call it 88.5 so I can fit it in here better. So I'm going to say, okay, I've got this sample and it contains 84.5. What am I saying? 88.5? 84.5 grams of MgOH2. And then we have some other amount, which is just junk. Yes? And I want to, and this 84.5 grams, 84.5 grams is 88.5% of the total. Yes? So 88.5% of the total is 84.5. So I'm going to call this entire amount here, so this entire thing, I'm going to call that X. So 88.5% of X is 84.5 grams. Does that make sense? Okay. And what does OV mean? OV means multiply. Oh, look, 0.885 times X. Yes, of X. 0.885 times X. So I've multiplied and we get 84.490. And now we can just solve for X. Is good? Okay, so you would just do the algebra and solve for X and you get 95.5 grams. And that would be like the entire thing in the green box. Okay, so that's the mass of the magnesium hydroxide and whatever other junk there is. So once again, it's kind of like interpreting the problem and just knowing how to work with percentages. So there's nothing really difficult about it other than the fact that you need to interpret it and work with the percentages. Okay, lastly but not leastly, here we have another example. Calculate the percent purity of a sample of MgOH2 if a titration of a 2.568 gram sample, so that would be our, actually I should make that green because that's our impure. Required 38.45 milliliters of means times, 0.6695 molar H3PO4. So the first thing we're going to do is we're going to say, I need to find moles of H3PO4. And I can do that from my milliliters and my molarity. Yeah? So I'm going to change the milliliters into liters and multiply it by 0.66595 moles of H3PO4 per liter. That gives me moles of H3PO4. Now I want to know how much MgOH2 is needed to react with that. Well, I have a 3-to-2 ratio. 3-to-2. So that cancels out that. Now we have moles of MgOH2. And we have 58.3 grams of MgOH2 per mole. And we get 2.2516 grams of MgOH2. Now, remember, does the junk react with the H3PO4? No. Only the pure, get rid of this one, MgOH2 reacts. So now we know the mass of the pure MgOH2. We're asked to find the percent purity. If we know the pure mass, what else do we need? We need the total mass. Okay, so let's go back. That should be given in the question. And lo and behold, oh look, it is. This is the total mass of the MgOH2 plus junk. And so we're going to take our pure mass and divide by the total mass, the impure mass. Okay, so we're going to take pure mass and divide by our impure mass times 100, and we get 87.68%. Okay, and there's just a bunch of questions on the next page. So we took some time in class during period 1 to work on these, and then I gave them like some sample problems that you might, I was like, if you just want to figure out what you want to work on over the weekend from 7.1, 7.2, and 7.3, you do not have to specifically do this. Yeah? But someone asked me to pick out some problems, so I'm like, okay, these are sort of possibly representative of things. Yes? And one involves Hebden, so make sure you know where to get Hebden from, either if you need to sign out a copy or know where it is on Teams. Yes? Okay, cool. And we're just going to work on these for the rest of the class, and that's it. Isn't that nice? Okay? You look stunned. Yeah. Yeah. Oh, something that we talked about in the first class, someone mentioned that percent purity is to do with the reactant. Percent yield is to do with the product. Percent purity is to do with the reactant. Percent yield is to do with the product. And if you get bored with this, you can go and work ahead on 7.4, because if you're like, okay, I understand all of this, it's all good, don't need it, don't need practice. 7.4 just throws in enthalpy.
Wait, Dorothy.
Yeah, if you're bored, you can try the challenges on page 79.
What?
I'm gonna turn this off because it's only producing more heat and it's already like disgustingly hot.
I
across the
literally
classroom.
wore a knit sweater and I thought it would be.
Well, I thought it was gonna be freezing too, so I wore long sleeves, right?
Now
I'm like,
I'm dying.
oh.
This is fine.